strong acids, if you can get your notes out. You also want a data booklet in front of you too. All right, so folks, good morning. We're going to start with some notes this morning, and then we're going to move on to the acid-base worksheet number 2, the acid-base concept number 2. Despite my repeated exhortations, there were still, I don't know, 5, 6, 7, 8 people in, actually more than that, I think, in this section who didn't hand in their equilibrium supplementary problems, okay? So we were told if they weren't handed in by Friday, you'd get a 25% deduction, by Sunday night, a 50% deduction, and you still didn't hand anything in. And there's a number of other people who aren't doing any ed puzzles and things like that. That's adding up. Now, for some of you guys, your mark is sitting in the 50s. What's saving you is your assignments. So when you suddenly don't hand in a whole set of problems for a whole unit and don't do 3 or 4 ed puzzles in a row, that 50% mark is going to go down, isn't it? And you don't have much wiggle room, right? So that's not very smart. And for other people who are wanting to get some particular mark for scholarships or whatever else, when you suddenly don't hand in 3 or 4 assignments, don't do them, again, you're just throwing away points, right? And then there's the obvious correlation. If you don't do your homework, how are you going to do on a test, right? So you're kind of just in a spiral here, aren't you? So if you did that in the equilibrium unit, you know, you can start fresh, okay? The acid-base unit. Don't fall behind in your homework, right? And get things handed in. Start fresh, all right? Don't keep digging a hole, right? What's the advice when you're digging a hole? What are you supposed to do first? Stop digging, right? And then start getting yourself out of the hole, but stop digging. Okay, so start getting your homework done. And if you've dug a hole and you want to talk to me about it, do that, but don't throw away easy points. Okay, so the ed puzzles that were assigned last week, I was feeling unwell for much of the week. I was tested negative, but still couldn't come back because of a sore throat and things. So the ed puzzles, that's me trying to teach you when I'm not here, right? So I'm not going to now just go back and teach all that. So if you didn't do those things, it's like you missed 3 or 4 days of class, right? And you've dug a big hole. Go back and do those things. I'm moving on. All right. So today we're going to look at strong acids and weak acids. And just a heads up, I'm going to have to be running back and forth a bit to the room next door. There's an AP exam. So I have to go in just a moment to read some instructions to the kids, and then I'll come right back. Okay. So we're going to look at equilibrium kind of problems. I told you before, this unit is like an equilibrium unit. You're about to see that today. Okay, so I'll share the screen here. We're going to spend 2 or 3 days looking at acids, how to calculate the pH of different acid solutions. And as you can see from my notes in front of you, it's going to be ice tables and equilibrium, right? So today we're looking at strong acids and weak acids. So write that title down, the pH of strong acids. And then the example there is nitric acid, but it doesn't matter. It could be any strong acid, and it would be done exactly like we're going to do this. Then we're going to move on to weak acids, which are a little bit more complicated. All right. So in the example here, we have 0.10 molar nitric acid, HNO3. If you have a data booklet, look up in your Ka chart, HNO3. and prove to yourself that it actually is a strong acid, right? Now I'm going to go next door to read some instructions. Once you've proven to yourself it's a strong acid, copy down the equation, the reaction that's happening, and we're going to fill in an ice table underneath it. I'll be right back. All right, so you saw that nitric acid is a strong acid because the Ka value was large, right? So any of those acids in your data booklet that are at the top, where the Ka just says large, those are all strong acids. And it wouldn't matter which one we had, we would do exactly the same thing we're going to do here. We always write the acid reacts with water. Okay, the acid's dissolved in water, but it reacts with water. Some people try to memorize. If you memorize, you're going to get overwhelmed. There's too much to memorize. So understand it. What does an acid do? It donates hydrogen. So HNO3 gives hydrogen to the water. H2O will then become H3O positive, the hydronium, right? HNO3, if it lost its hydrogen, now it's just nitrate. That's its conjugate base, isn't it? Fill in the initial line of the table. Well, we were told it was a 0.1 molar nitric acid solution. So the nitric acid starts off at 0.1 molar. The water, you remember it's a liquid, right? So you might want to remind yourself of that. Water is a liquid, and because it's a liquid, it's not going to be in our equilibrium expression. So we're just going to put a big X under it, right? Make sure you know why we're putting an X under it, because it's not going to be in the equilibrium expression. It's a liquid. Hydronium is a little complicated. I'm saying that it starts at 0, but technically that's not true, right? Can someone tell me why the hydronium is actually not 0? Anybody? Yep. Exactly. The water molecules that are there, they react with each other, right? The self-ionization of water. What's the pH of water at 25 degrees? What's water's pH?
7 pH.
It's 7, right? Yep. And why is it 7? It's 7 because in pure water, there is 1 times 10 to the minus 7 molarity hydronium, right? Because of water self-ionization. So technically, the hydronium is not 0. It's 1 times 10 to the minus 7. But that's such a small number. It's so small. This acid is going to give us lots of hydronium. The initial hydronium, the 1 times 10 to the minus 7, is so small that if we put it, we're just going to round it off. It's going to get rounded off, and it's going to have no effect. So it's basically like saying it's 0. There is no nitrate. Nitrate is 0. Hello. Sure.
Hi guys, we're just gonna hit grade 12. Can you raise your hand if you're in grade 12? You just have a information sheet about the grad book.
About grad books?
The grad book. Yeah.
So it's just like a list of fundraisers and that you need to take if you want.
There's information if you want to send them for this on the communication book. Valedictorian auditions are opening. On the back, we have this little sample of what you're They're just like a paper.
And are you guys coming back for the next 2 days to do it again?
Yeah, the other questions.
Okay. So for those of you at home, they're handing out some stuff about grad, but you'll get it the next time you're at school, I guess. Thank you, folks. All right, so hydronium technically is not zero. You should probably note that on the side. All right. The nitrate is zero because there is no nitrate in water, right? But there is hydronium in water, but it's so small, we're going to say it's basically zero. Now, once you've filled in the initial line of your ice table, go to the side of the table and describe the acid. Okay, describe the acid that we have here. What can we say about HNO3? Well, we know it's a strong acid. What does that mean to say it's a strong acid? Well, its Ka is large. And what does it mean if it's strong and it has a large Ka? What does that mean? That's important here. It means it ionizes completely. That's the important part. So nitric acid is a strong acid. It has a large Ka value. And the important part is that means it's going to ionize completely, 100%. Why was it important to think about that at this point when we're filling in the ice table? Because now when I think about the change, I know exactly what's going to happen. If you started with 0.1 molar nitric acid, but it ionizes completely, what's going to happen to that 0.1 molar? It's going to lose all of it, right? So you're going to lose all of the 0.10. So you see how you're thinking about it and you're not just memorizing? It makes sense, doesn't it? Now, acid-base chemistry is simple because the ratios are all 1 to 1 to 1. That's also bad because when we finish acid-base chemistry and we go back to ratios that are not 1 to 1 to 1, everybody forgets, okay? But the balanced equation here is just a 1 to 1 to 1 ratio. So if you lose 0.1, the others are going to gain 0.1, right? But don't forget, it does depend on the ratios, doesn't it? If there had been a 2 hydroniums, that would have gained 0.2, right? So don't forget that. So fill in the last line. You have 0, you have 0.1 and 0.1. And if you're thinking, you know the problem's basically finished, isn't it? We want to know the pH. But pH is the negative log of hydronium. Hey, we now know the hydronium. So go get your pH. Right? So write down your formula for pH. I'm a bit lazy and I didn't write the formula, but write your formula down. The pH is negative log of hydronium concentration, square brackets. And we now know the hydronium is 0.10. So you could grab a calculator and please do it on your calculator. Make sure you can get it. But can't I also do that in my head? How could I do that in my head? Isn't 0.1 a very nice number? 0.1. It's a very nice number because isn't it just 10 to the minus 1? 0.1 is 10 to the minus 1. If it's 10 to the minus 1, then the pH is going to be 1, right? If it were 10 to the minus 2, the pH would have been 2, right? If it were 10 to the minus 10, the pH would be 10, right? So when you have a very nice number like that, you can just do it in your head. If the pH is if the hydronium is 0.01, you'd say, well, that's 10 to the minus 2. Oh, well, then the pH is 2. Done, right? If you don't want to do it in your head, just grab a calculator. Hopefully you get that answer. Now, if you think about what I just said, if it was 10 to the minus 1, the pH was 1. The 1 in the pH value came from the exponent, 10 to the minus 1. But that's not a significant digit. The exponent is not a significant digit. So the number 1 at the beginning of my pH, it's not a significant digit because it came from the exponent. Only what's after the decimal is considered significant. So when you have 2 significant digits in your concentration, 0.10, 2 digits, you should keep 2 decimals in your pH. That can be a bit confusing. If you don't want to think about that, just make a note, always put 2 decimals with your pH. If you always put 2 decimals, 99% of the time, that's going to be correct. Okay? Just don't put 1 decimal or 5 decimals. Just put 2 decimals with every pH. All right. Would this be a good electrolyte? Would this nitric acid solution be a good electrolyte? What does it mean to be, what's an electrolyte? Well, water does not conduct electricity because there's no electrons in water that can move around. And but there's also no ions. There's no negatively or positive charged ions that can move around. There's very little in water. So water doesn't conduct electricity. But if you have salt in the water, salt produces ions. Or if you have acids or bases in the water, then suddenly there's ions and the water conducts electricity. So those things are called electrolytes. They produce ions and conduct electricity. Does nitric acid make a good electrolyte? Well, you end up with 0.1 molar hydronium ions, and you end up with 0.1 molar nitrate ions. So you have 0.2 molar ions. That's a pretty big concentration, 0.2. So yes, this would be a very good electrolyte. It has lots of ions, so it would be a very good electrolyte. Okay. Notice it's not just because it's a strong acid, it was also because it was pretty concentrated. If it were a very, very, very dilute solution, well, then there'd still be very little ions, even if it dissociates completely, because there's very little acid to begin with. So whether it's a good electrolyte or not depends on 2 things. Is it strong or weak? And then how concentrated is it? You got to be pretty concentrated and be strong to be a very good electrolyte. Okay. Please ask folks if something doesn't make sense. Okay. All right. So that was a strong acid. Any strong acid, we would do exactly what we just did. Okay. Almost any strong acid. There's one exception to that, but we'll see that later. Weak acids. Can you tell right away why this is going to be more complicated? Yeah, they do not completely ionize. And that means when we fill the ice table in, we're going to run into a problem, aren't we? We can't just say it loses everything because it doesn't. It doesn't lose everything. And we don't know how much it loses. Oh, well then we're just going to use algebra, aren't we? We're just going to use X's. All right. So here we have 0.15 molar hydrofluoric acid, HF. Take a moment, look it up in your data booklet. If you're doing a homework question, it's not necessarily going to say it's a weak acid or a strong acid. You have to look it up in your booklet. So HF, if it's not at the top of the page, if it's not one of the ones that say large Ka, then it's a weak acid. So HF, the Ka is around 10 to the minus 4, isn't it? That's a weak acid. So go ahead and write a balanced equation. The acid is dissolved in water, so it reacts with water. It's always going to react with water. So write the reaction HF plus H2O produces, and think about what the 2 products have to be. Acids give away their hydrogen ions and bases accept the hydrogen ions. So you're going to get hydronium again, and you're going to get fluoride this time, right? Put the initial line in for your ice table. Okay, the acid is 0.15 molarity. The water is a liquid. We don't care about it because it's a liquid. The hydronium, just like before, it's so small that we're going to ignore it. Now, somebody might ask, well, what if the acid was really, really weak? Like really weak? Could the initial hydronium actually be important? The answer is, logically, the answer is, yes, it could be important. I'm not going to do that to you. Okay, so I will not give you an acid which is so weak that the initial hydronium would be important. We're always going to say 0. Okay, and there's no fluoride in water except our drinking water, right? Our tap water has fluoride because we add fluoride for tooth decay, but pure water, there's no fluoride. Go to the side of your ice table and say something about the acid. Describe the acid on the side of your ice table. When you're describing it, write down the Ka value from your booklet. So this, you're not going to just say it's a weak acid, you'll write down the Ka value. On my PowerPoint, I used an old Ka value from a different chart here, but then I fixed it in just a minute. So don't just copy what I'm writing here. This Ka is from a different source, but I fixed it in the next step, okay? So because it's a weak acid, small Ka, say something like I did, it does not ionize completely. It does not dissociate completely. So what am I going to say on the change line? What do I say under 0.15? Yeah, we don't know how much it loses, right? So we'll say minus X. And what will we say for hydronium and fluoride? Well, it's a 1-to-1 ratio. So those are just going to be plus X, aren't they? So minus X plus, and it makes sense, doesn't it? If you understood equilibrium, this makes sense. And if you understood equilibrium, you know what we're going to do next, aren't we? Right? If we have X's, don't we need to write a Ka expression and put it in and solve it? So go ahead and do that. Write your Ka expression, write the equilibrium expression, put the algebra in. If you own a graphing calculator, go ahead and solve it. If you don't own a graphing calculator, look at it. It's going to be irritating. Folks, why am I hearing beeping? Whose phone is beeping every 2 seconds? Okay. So there's your Ka expression. You left the water out, I hope. And you put your algebra in, and that's where you get. And if you have a solver and a graphing calculator, you're home free. For those of us without the graphing calculator, do we see something here that's scary? Do we see something here that makes us nervous? In the equilibrium unit, we just square rooted both sides, right? Can I do that here? Can I square root both sides? I could, but it would be dumb. Don't. Why would you not square root both sides? Well, the top is squared. That's good. But the bottom is not squared. So square rooting is going to be bad. If you square root this, the bottom will be trapped under a square root symbol. You can't do anything with that. So we have a problem, okay? I'll give the people with the calculators just a moment to finish if they're using their solver. And then I want everybody to watch how we're going to solve this. Not just watch, but okay. All right, so there's two ways we can solve this if we don't have a graphing calculator. One way, if we feel brave, would be to do algebra, and we can take the Ka and we could times it by the stuff on the bottom, and that would equal the stuff on the top. And if you think about that, that's going to create a quadratic equation. It's going to create x squareds and x's and numbers. Well, we know how to solve quadratic equations. If you've taken grade 10 or grade 11 pre-calculus math, you know there's a quadratic formula. You could solve it. That's scary. I don't want to use a quadratic formula. I don't want quadratic equations. We will never have to do a quadratic equation, okay? There's another trick we can use. It's got a name. I'm going to say it, and if you're at home, you can write down what I'm saying. I'm going to write it on the board here. It's called successive approximations. Okay, successive approximations. The word successive means repeated. Repeat once, twice, three times, do it over and over again. That's what successive means. Approximations, well, we're going to get answers that are not correct, but they're close. And if we do it repeatedly, successively, we will get answers that are closer and closer and closer to truth. We don't need truth. We don't need 10 decimal places of truth. We're going to round off our answers. So this method will work if you want to do it over and over and over and over again for the next 2 days. You could get the correct answer to 50 decimal places. We only need to do it 2 or 3 times, and we'll get the correct answer that someone with a graphing calculator gets, because they're going to round it off. Okay. So here's how it works. Understand it. Don't just memorize. We agree the Ka is small, right? What does that mean in terms of equilibrium when a Ka is small? It means you don't make much product, right? The amount of product will be small. Another way of saying it, it means that what you lose, the 0.15 is losing X. What you lose is very small because Ka is small. If I have $1 million, right? I have $1 million, I'm a millionaire, and I give Evan over there $5. Right? I have $1 million, but I just gave away $5. Am I now depressed because I'm no longer a millionaire? No, I'm not depressed. In fact, I'm still going to call myself a millionaire, right? If I have $1 million and I gave away $5, am I now going to say, well, actually, I have 995. I'm just going to say I still have $1 million, right? $1 million take away 5, it's still $1 million. Do you see how that applies here? 0.15 is way bigger than X. So when you have 0.15 and you subtract X, how much do you have left? Pretty much 0.15. Pretty close to 0.15. So here's what we're going to say. We're going to say, because the Ka is small, and you have to say this in your answer, by the way, you can't skip this step or you lose a little half point. Because the Ka is small, let's assume, there's the approximation part, because we're going to assume that X, I'm going to use 2 less than symbols. 2 means much less. Okay, we're going to assume that X is much less than 0.15. Now, the smaller the Ka value is, the better that assumption is. The bigger the Ka value is, the worse that assumption is. If it's a really good assumption because the Ka is really small, then we really will probably have to just do 2 approximations and we'll get the answer. If it's a bad approximation, then you might need to do 3 or 4 or 5 approximations to get the right answer, okay? So here we go. What does it mean if x is much less than 0.15? Well, as we just said, 0.15 minus x would be around 0.15, wouldn't it? So rewrite your equation. Then 7.2 times 10 to the minus 4 is approximately equal. I'm putting a squiggly equal sign, right? That means approximately equal to x squared over 0.15. Please stop me right here and ask if you don't understand what I just did there. Okay? Do you see how this is now very easy to solve? Do you see how anybody could solve this on a calculator? This number out front times the number on the bottom is going to give me x squared, isn't it? So grab your calculator. 7.2 times 10 to the minus 4 times 0.15 equals. Do that on your calculator right now. 7.2 times 10 to the minus 4 times 0.15 equals. Now look at the algebra. What does this number equal? It equals x squared. So you now need to take a square root, right? So square root the answer. Did you get 0.010 on the calculator? Anybody not get 0.010? Ricardo, you didn't get it? So on your calculator, clear everything on your calculator. Do 7.2 times 10 to the minus 4. So make sure you're using the scientific notation button, right? 7.2 times 10 to the minus 4 times that by 0.15, right? So multiply by 0.15 and press equals. Does your calculator now say 1.08 times 10 to the minus 4? This is equal to x squared. X squared. So now I have to square root this answer. Do you know how to square root on your calculator? So take the square root of this answer. My calculator says 0.0103. Does yours say that? 0.0103, if you round it off, is just 0.010. Okay? Do you notice I didn't say that that's equal to x? I said it's equal to x1. What was this called, this method? Successive approximations. This answer is my first approximation. It's not the best. This is my first. Now we're going to get a second approximation, and the second approximation will be better than the first, right? And if you do a third, it'll be better than the second. It keeps getting better and better when you do these approximations. I'm not going to show my work, so you have to do it with me on your calculator, okay? So I never show my work for this. I just do it on a calculator. You go back and look at the original equation over here. Notice we ignored the minus x, didn't we? We ignored that, and we just made it 0.15. So what I'm going to do is I'm going to take this first answer, and I'm going to put it where I ignored it. I'm going to put it back down here. You with me on that? So let's do that on our calculator. Type in 0.15 minus the first answer, 0.01. David, do you not have a calculator with you? Do you want to grab a calculator? Okay. Here. You can use mine. Okay. So you're typing in 0.15 minus your first answer, 0.01, and press equals, right? It's 0.14, isn't it? 0.14. So imagine this other equation over here. Imagine that this now said is approximately x squared over 0.14. So solve it again. Take your answer, 0.14, times it by the Ka value and press equals, and then square root. So take that 0.14 and times it by 7.2 times 10 to the minus 4, press equals, then square root the answer. That answer is your second approximation. When I did it, it was the same as the first. Anybody not get that as their second approximation? If it's the same as the first, you're done. We're finished. For those of you that use the graphing calculator to solve this, isn't that the same answer you got with the solver? Anybody use, yeah, I see someone nodding over there. So if you use the graphing calculator, that is the answer you get with the solver. It usually doesn't work out like that. Usually your second approximation is a little bit different from the first. So suppose my second was not 0.01. Suppose it was 0.012. So what do I do if it's not the same? If it were different, I would take the second approximation and do exactly what I just did. I would put it back on the bottom over here, 0.15 minus the second approximation, and then I would do it again. I would solve again. I'd get a third approximation. And I would do that over and over again successively until it stayed the same. Does that make sense? So the answer is your first approximation is like you're shooting at a target and you were on the left, you missed it on the left. When you do a second approximation, you miss again, but you're now on the right-hand side, but you're closer. If you do a third approximation, you're going to be on the left-hand side again, but even closer. And if you do it over and over and over and over again, you get closer and closer and closer and closer and closer to the right answer, to exactly what someone would get on a solver, to 20 decimal places. Okay? It actually takes about 2 minutes, less than 2 minutes, to get the answer. And it's faster than doing the algebra and the quadratic equation. Okay? All right, finish the problem. X is our hydronium concentration, so go calculate the pH. If there's anybody who was not able to get the second approximation, please ask me and I'll try to talk it through with you. Whenever you do it, please write your formula. In my notes, I was lazy and I didn't put the formula. The pH is the negative log of hydronium. Then show your work. This is another one we could have just done in our head. 0.01 is 10 to the minus 2. So the pH is going to be 2, 2.00. All right. That is a typical weak acid question, right? If instead of hydrofluoric acid, I had asked acetic acid, it would look exactly the same. The problem would be exactly the same. Any weak acid question, that's what you'll do. It's very similar, okay? Now we agreed this acid did not ionize completely, right? It did not ionize 100%. You had 0.15 molarity, and how much actually ionized? 0.01. So can you tell me what percent did ionize? What was the actual percent ionization for this acid? It was not 100%, but what was it? Well, what do? This is not some high level chemistry. It's just percent, right? So Riley, what am I going to do to find this? But what am I going to do to find it?
Divide the
Yeah, take the, well, not the ending, but the change, right? So take your change, which in this case was 0.01, right? And divide that by your starting amount and times by 100, okay? So I did not show a formula for this. You might want to label these things in your notes. 0.15 is the starting concentration. 0.01 was our X value. That's what was lost, right? That's how much ionized. Does it make sense that this is how you would find percent ionization? If I asked you what percentage of your money did you spend, wouldn't you take the amount you spent and divide by your starting amount and times by 100? So what percentage of your acid ionized? Well, take the amount that ionized, the X value, and divide by the starting amount and times by 100. It's just logic. It's not a chemistry thing. So it wasn't 100%. It wasn't even close. It was less than 7%, right? Sometimes this is called percent dissociation. You hear me use those terms. They're the same thing, right? Ionization, dissociation, they mean the same thing. So if you see one thing, it means the same as dissociation, okay? So one way to think about that would be 6.7 out of every 100 molecules, but 6.7, you can't have a fraction of a molecule. So how about if you just times them both by 10? Instead of 6.7, you'll have 67. Instead of 100, you'll have 1,000. So 67 out of every 1,000 molecules are ionized, right? So in a weak acid, most molecules are not ionized, right? Over 900 and something of the 1,000 molecules did not ionize. Would this be a good electrolyte? No, right? It's not a good electrolyte because it has very little ions, right? It's mostly unionized. All right, let's stop there and turn to the second worksheet on acid-base concepts. It's around page 100 or something. Page 130, rather. Acid-base concepts number 2. We're not going to be able to finish this page today. Whatever we don't finish, can you try to finish it tonight? Everything on this page, both sides, we now know how to do, or we should know how to do. Okay. So question 1, go ahead and write the conjugate acid or base for each one of these things. You remember the word conjugate just means your partner, right? Conjugate is your partner. If you're an acid like HNO3, then Bronsted-Lowry told us acids lose hydrogen ions. Bases gain or accept or add hydrogen ions. You don't have to draw that, but you might want to draw a double arrow like that. An acid loses the hydrogen ion, the base adds the hydrogen ion. So if I give you something and say this is an acid and ask you what is its conjugate base, lose a hydrogen ion. So HNO3 will become NO3, but it's losing a hydrogen positive. So this is going to now be negative, isn't it? If I give you a base and say, what was its conjugate acid? You do the opposite. You add a hydrogen ion. Okay, now over here, the hydrogen ion is going to add to the nitrogen, not to carbon. Okay, so you're going to get CH3 and then NH3, and you're adding a positive. So this thing was neutral, so this is going to be positive, isn't it? If you're not sure why the charges are what they are, you should stop me and say, explain that again. The next one is acetic acid. I want to take a little detour on this one. Go to the side here and let's draw the acetic acid molecule. I want to show you something about it. Grade 11 organic chemistry, you might remember doing this. CH3, C double bond O, and then OH. That's acetic acid, CH3, COOH. If you have your data booklet with you, turn to your table of electronegativity values. Dennis, if you're still there, I will be posting it for you. That's fine. Turn to your electronegativity table right after the periodic table in your data booklet. Remind yourself from our first unit, if you have a bond between carbon and hydrogen, is this bond non-polar covalent? Is it polar covalent, or is it ionic? It depends on the difference in electronegativity, doesn't it? If the difference is less than 0.4 or 0.4 or less, it was non-polar. So look at carbon and look at hydrogen. Is the difference between them 0.4 or less? Yes, it is, right? It's a very small difference. So then let's label these bonds. This bond, and this bond. These are all non-polar covalent bonds. The difference in electronegativity is so small that the electrons are shared equally. They're non-polar covalent. But what about the OH over here? What about oxygen, hydrogen? Look up those guys on your electronegativity table. Isn't the difference now bigger than 0.4? It's bigger than 0.4 difference. Is it bigger than 1.7? If it's bigger than 1.7, it's an ionic bond. It's not bigger than 1.7, right? But it is bigger than 0.4. So this bond is a polar covalent bond. And what does it mean to be polar? It means that the electrons are pulled towards oxygen because oxygen is more electronegative. So oxygen, because it's pulling the negative electrons towards it, becomes partially negative. We use the Greek letter delta, right, for partial charge, partially negative. Hydrogen is going to become partially positive because it's losing its electrons a little bit. That's what a polar bond is. Now off to the side, let's draw a water molecule and draw it exactly like you see me drawing this one. There's H2O, there's a water molecule. Isn't it also polar? Because it has these OHs in it, OHs. So this oxygen is partially negative. These hydrogens are partially positive. And do you see what I'm about to show here? The hydrogen in acetic acid over here is positive. The oxygen in water over here is negative. So what's going to happen? They're attracted, aren't they? And so what does water do to that hydrogen atom? Water will pull it away. And there you get hydronium, right? The water takes this hydrogen because they're attracted. Does water take these hydrogens over here? Does water take those hydrogens? No. Why not? Because those are non-polar bonds. Those hydrogens are not positive. Water will ignore them, right? So even though acetic acid has 4 hydrogen atoms, only the one that's bonded to oxygen is going to be attracted to water because it was part of a polar covalent bond. Okay? So coming back here, CH3COOH, there's 4 hydrogen atoms, but only the one bonded to O is the one that's given away. So this will become CH3COO minus, right? The H's bonded to carbon do not get donated. When you see something like HNO3, you could be forgiven if you thought that that hydrogen is bonded to the nitrogen. It looks that way. It isn't. Nitrate is this. Nitrogen, actually, it's like that, a single bond. That's a nitrate ion. The hydrogen ends up bonding to the oxygen in nitric acid. Carbonate is like this, CO3, and the hydrogens bond to the oxygens, right? So they don't bond to carbon, they bond to the oxygens. Now, CO3 is 2 minus. It's going to accept the hydrogen and become HCO3. And what's its charge going to be? Minus, right? 2 minus. If you go up by 1, goes up by 1 positive, it becomes 1 minus, right? All right. Question 2. This is very important basic math in this unit. Hydronium, hydroxide, pH, POH. If you know one of them, you know all of them, right? So let's do this guy here. We have 0.0052 molar hydroxide. We're going to find the other 3 things. Which one of those 3 things can I not find right away? Which one of those other 3 things could I not find right away? The pH.
H3O.
We cannot find pH right away because pH, you would need to know either the hydronium or the POH, right? But I can get the POH or I can get the hydronium. I can get either one of those right away. Personally, I like to do this guy first. Okay, you don't have to. You can go do hydronium first, but I'm going to do this guy first. The definition of POH is the negative log of the hydroxide. I know the hydroxide, so just plug it in. Grab your calculator. Okay, I gave my calculator away. Can someone tell me the answer for that? .28. Okay. Can you notice something? 0.0052 is a reasonably large concentration of hydroxide, right? Neutral would be 10 to the minus 7. That's much bigger than 10 to the minus 7. So that tells me this must be basic because it has lots of hydroxide. If you have lots of hydroxide, your POH will be low. Just like when you have lots of hydronium, you're an acid, your pH is low, right? So when you have lots of hydroxide, POH will be low. If you have lots of hydronium, pH will be low. If your POH is low, then your pH will be high, right? Because they're sort of almost like inversely related. So let's go calculate pH. We can do this because we know pH plus the pOH gives me 14 at 25 degrees Celsius, right? Where does the 14 come from? Why does it equal 14? It's 14 because the kW value is 1 times 10 to the minus 14. That's where that number comes from. So then the pH is going to be 14 take away the pOH. And we're done. 14 take away 2.28. When you have a very low pOH, you're going to have a pretty high pH. When you have a pretty high pH, you're basic, aren't you? That's a basic solution. What about your hydronium? Well, we can get this in two different ways. One, we could use the Kw expression. Kw, the equilibrium constant for water's dissociation, is 1.00 times 10 to the minus 14, and that will equal the hydronium times the hydroxide. So if you know the hydroxide, you just have to take the Kw value and divide by your hydroxide, and you'll get your hydronium. So that's one way to do it. Or if you want the hydronium, can't you use the pH to get that also? You could say the hydronium is 10 to the power of negative pH. Personally, that's what I like to do. 10 to the negative pH. So that's going to be 10 to the power of negative 11.72. That's going to be pretty close to 10 to the minus 12. This is going to be a very small number. So grab your calculator. 10 to the power of is right above the log button, isn't it? On your calculator, there's a log button. Right above the log button, it should say 10 to the x. So you want to go second function log, and then you'll type negative 11.72. What do you get? And this is a concentration, so we should say molarity, right? pHs and pOHs don't have any units. They're logarithms. They don't have units. All right, folks, it's 12:14. I'm tired. We almost got to the same part as thought A, but I'll stop there. Can you try to finish this sheet tonight? You're probably going to struggle a bit with these questions. There were some questions like this in the homework also. People always struggle with those. I will discuss them tomorrow. So if you're not sure how to do those, just hold off and we'll discuss it tomorrow. But try your best to finish this off tonight, okay? Have a good evening for those of you at home. We'll see you.
Are we allowed to ask questions for the supplementary problems?
Can we hold off on those until tomorrow? Is this Kale?
Yeah.
Kale, if you have a quick one or two, I can take it, but otherwise we'll do some more tomorrow.
Yeah, it's just about 5 and 6.
5 and 6. Let me take a look.
So would that mean the supplementary problems are still due today or
No, I'll give you an extra day or two.
Okay, thanks.
So 5 and 6.
Sorry, I'm just flipping to the page.
I've got them right here. You should be able to see it.
Okay. For 5C, do we like take all the H's away from CH3COOH?
Remember, we just talked about that today, right?
Yeah.
So acetic acid, although it looks like it has 4 H's to donate, how many H's actually get donated?
Oh, it's just the last one. Okay.
Just the one. So it's a monoprotic acid, right?
And then for 6, do we write the Ka expression for each step or just the last step?
If it's a polyprotic acid, you should do it for each step.
Okay.
It
Yeah,
kind
that's
of-
all I needed.
Kind of irritating, but yeah.
Yeah.
Okay,
Okay, thank you.
you're welcome.